Okay, so for Lab 2, the main concepts were conversions between the metric units, concentrations, some dilutions, and that V1, C1 equals C2 and V2. And some data, how to do data distribution. So to begin, essentially the conversion units, they always follow the same pattern. So in our case, if we have 0.5 mils of water, for example, that's the same thing as 500 microliters. Oops. It's just the same as when we use concentrations. Remember, concentrations are just substance over a certain volume. So how tightly packed is a certain substance in a certain space. This can be moles for liters, and that's molarity. This can be as simple as micrograms per microliter of protein, for example. So definitely, I would say know the conversions that we usually use for water. So if you have, if you're using 2 microliters, remember that this is equal to 0.002 mils, for example, things like that. And you should be fine. And remember, the concentrations can be labeled the same way. So let's just work through an example problem. Say we have an 8 millimolar stock. And when you see stock, just assume you have infinite amounts of stock. So don't worry about the volume you're taking out. So that's our C1. We need to get down to a 2 millimolar solution. So that's the concentration we need to get to. And the solution needs to be in, I think, what did I put it as? I think 100 microliters. That's our final volume. Okay. So we have elements of the V1, C1 equals V2, C2. We know that we're going to try and get after this volume 1. We need to know how much of this stock to take. So we can do the algebra, move our C1 down here. V1 is going to equal 2. And remember, these have to be in the same numeric value, so they're both in millimolar. So 2 millimolar, and then V2 is 100 microliter, and that's all over 8. So that is 200 divided by 8. Oh no, what have I done? So that's 25. So that means V2, or no, sorry, V1, so the volume from the first stock solution, because this is C1, is going to be 25 microliters. So what that means is that from your stock solution, you're going to take 25 microliters of that concentrated 8 millimolar, and you're going to fill it up with 25, but you have to get to 100, so the other 75 just comes from water. And now your total is 100 microliters, and your concentration is now 2 millimolar. So if you want to shorthand this, if you see problems like this, and if you need to take an 8 to a 2, for example, you essentially can just you can see how this is kind of a fraction, right? How we went down 4 scales, we divided it by kind of into 1/4, and that's what happened up here in the equation too. So if you can do it shorthand, that saves you time, obviously, but you don't have to. You can just use V1, C1 for anything if you really want. Okay. And remember that 1 mole of substance, and this is, this has to do with Avogadro's number and how big the actual chemical is. So 1 mole of substance equals the molecular weight in grams. So 1 mole of NaCl, which weighs 58.33, I think, something like that, 44. So 1 mole of NaCl equals the molecular weight in grams. And you can add up molecular weights. I don't think you're going to have to, but that means that 3 mole of NaCl is going to be 3 times the molecular weight, whatever 3 times this number is. I don't have my calculator. And you won't need to do, you know, complex stuff like that, so you should be fine. Okay, and then after that, in this lab we did the dilutions, we used the spectrophotometer for the first time, and essentially remember your little spectrophotometer, you have a certain nanometer of wavelength that's gonna go through, and then one that's gonna be read, and then what's going through. Depending on what's in here, if it's like a dense blue, like we've seen, very little light is gonna get through. However, if it's just water and it's very clear, then a lot of the light's still gonna get through, a lot of that nanometer wavelength. But remember, we have to blank things because the plastic and the water, they do absorb some. So it's kind of like blanking a scale. If you're measuring something on a scale, but it has to be in a container, you only want to measure what's in the container, not the container itself. Okay. And when you have data, I think this covers, let me take a look. Yes, this is when we did the beans, I believe. So most beans, for example, they were at like 0.37 grams. So the range between 0.37 and like 0.39 grams, that was like the highest one. Sometimes the beans were smaller than 0.37, but those beans got less and less common, all the way to the smallest beans that were only like maybe 0.2 grams. Same could be said for beans that were over 3.9 grams. They were a lot, but there weren't like a ton. And they got more rare to be bigger. So right here, you'd have beans that were like 0.6 grams or something. So these are the extremes. This is the middle, because most beans lie within this range or near it. And this is what we get, a histogram bell curve. And this is just in stats. This is essentially just saying, here's our average, and here are our extremes. And this is normally how data distributes when you're taking a look at just generalized things. Sometimes things can shift one way or the other, but ultimately, you usually end up with a bell curve for data.